All right, well, it's my great pleasure to introduce Alberto Rodriguez. Alberto is a longtime friend and colleague and an academic sibling from the same lab, although many years later for him. Alberto is the class of 1957 associate professor at the Mechanical Engineering Department at MIT. His lab is called the MCube lab at MIT. They work on manipulation and mechanisms. So Alberto's got lots of awards to his name, and I won't try to name them all, but I'll name two that are particularly recent and relevant. Alberto's work in the Transactions on Robotics published last year, received the Best Paper Award just a few months ago for 2020. And then also last year, Alberto was named the Early Academic Career Award winner for the IEEE Robotics and Automation Society in recognition of all the great things he's done as a PhD student and as a professor at MIT. I know that our group is very inspired by the work that he does in robot manipulation and tactile sensing, tactile dexterity. And today, Alberto is going to tell us about the role of manipulation primitives in building dexterous robotic systems. And so with that, I'll turn it over to you, Alberto. Thanks very much. Let's please welcome our speaker. Thanks, Alberto.
Thank you, Kevin, for the very kind introduction. I have to. I'm obligated to say that we have likewise been truly inspired by a lot of work that happens in Kevin's lab, or that has happened for many years. So we're just continuing a lot of work that has been done for many decades now in trying to reason explicitly about contact. And today I wanted to talk about manipulation primitives. I guess that's excuse. Really, I want to talk about manipulation in general, and that will be the theme of the first part of the talk. Try to describe a few different approaches that I would say are complementary, that the research community has embraced to tackle this very complex but this very promising technology of manipulation, being able to change the world around us and bend it to our will. And then I'll go more in depth into what I mean by manipulation primitives in the context of two projects that have recently happened in the lab. Oh, let me see if I can actually pass my slides. So this is the outline of the talk. I'll talk about these four different perspectives on robotic manipulation, and then we will go in depth into the role of manipulation primitives in integrating those perspectives in the context of these two projects: dexterity with tactile feedback and dexterity with the visual affordances. Okay, but before going into the meat of the talk and going into the actual research, I wanted to start with a video that I've actually have used quite a few times, I have to admit, in many talks throughout my my years as faculty and directing the manipulation lab, which has served as kind of an inspiration for some of the work that we do in the lab. And it's a very short clip where you will see my hand will go into the shelf to grab this book. And it just naturally sort of places itself on the side of the book and pulls the book and then swings the thumb on the other side and gets the book into a grasp, right? So at the time I was using this example to talk about the idea that manipulation is not a state that we plan for, it's actually a process, right? So there's a lot of grasp centrism that has dominated research in manipulation, like how do we grasp a certain object? But to some degree, in many instances, that's the least interesting part of what's happening in manipulation is the process, for example, in this case, that leads into a stable grasp of the book. What it is difficult to replicate with the same naturality that we do it without thinking. So I thought that I would use this example to illustrate 4 different ways by which I think that not the only ones, but I think that have dominated our understanding of the manipulation problem. And I would like to start with mechanics, right? So someone might say, well, what makes this problem difficult, the reason why it is complicated to program a robot to do something as natural as extending the hand and swing the book from the shelf, is that the book doesn't have boosters that we can control, right? So a manipulation is an action that is done through friction and through contact that has complicated mechanics. You can only push through contacts, and friction has some hybrid behavior, sticking, slipping, and formulating control problems that can reason about all of that complexity is both a challenging and an interesting problem, right? So someone might say, well, the way to solve that problem or to address that problem is to think of a low fidelity model. Let's say I'm going to think of the palm as a quadrilateral, these sort of 4 points here with friction points, with friction cones associated with them. And likewise, I'm going to think of the book as another plane with friction cones, but now looking onto the wall, and the thumb has another friction cone that is that it can apply forces on the side of the book. And all of that sort of defines a set of constraints that ultimately defines a control problem. And reasoning through all of those constraints and how to come up with trajectories to extract the book, that has attracted a lot of attention. I would say that Kevin Lynch is, for example, one of the person that has sort of done groundwork on understanding how to formulate those problems, usually in the form of some optimization framework, and then control them. And then someone else might say, you know what, Kevin, why do I care about friction cones and contacts if ultimately everything that's happening in reality is dominated by microscopic changes on the texture of the object or the material properties? How am I even know the coefficient of friction you have to use? In reality, what is difficult here is understanding how can I actually render real forces. I want to transmit a certain force or a certain motion to the book through a contact that is not an actual plane or an actual point, is something that is conformable, my palm. And really what's complicated here is the notion of haptic. How do we control haptic feedback, right? How do we render real interactions with real objects? Once you know how to do that, it doesn't matter if you model the palm with 3 points or 4 points or with a larger friction cone or a smaller friction cone. If you can dominate, if you can solve that low-level control problem of rendering real forces through my end effectors, I can address many of those problems. But then someone else might say, well, if you look in detail at what's happening when I extend my hand, I contact the book. One of the things that is challenging for either low-level haptic control or from a control mechanics perspective is that this action actually goes through 3 distinctive stages, right? So first I slide the book, and in that phase, I exploit the fact that it's in contact with the side of the shelf until it gets to a point where the bottom of the book, it's pivoting about the edge of the shelf. And that is a different way of interacting with the book. And then once it's sufficiently outside, I do a dynamic swing to throw my thumb to the other side of the book before the book has time to fall, and then I'm on a grasp. So how do I plan through these distinctive set of stages where it is difficult to formulate as just one single control problem, but there's some discrete search that is necessary to be able to come up with this strategy to be able to extract the book. So that has also dominated manipulation for some time. But someone else might also say, actually, in reality, the book is not a real object, right? So what tells you that the book is different from the shelf itself? What you really see is just a set of pixels or a set of point clouds. And what tells you that the side of the book is a good place where to put the hand. What we would call sort of visual affordances or visual feedback how do we characterize sort of the appearance or the geometry of objects that are graspable or that are pushable, or where does it make sense to interface with those objects before knowing what's an object itself. And I would say that this last sort of has dominated manipulation in the last decade, or because of the uprise of neural networks and it's their ability to generalize or create biases or priors from examples. So there's these four perspectives that both stem from the same problem, and they both have been embraced maybe all throughout the last 4 or 5 decades. Maybe they have dominated a different decade themselves, but they've sort of have been used as a way to understand manipulation by the different part of the community. And as I said, sort of they're naturally come up because not just they're interesting, but also they characterize a certain challenging aspect of the problem, right? So we are interested in mechanics because the mechanics of that problem are underactuated and they delved into hybrid friction dynamical problems, or in haptic feedback because it is challenging to render real forces or velocity interactions with objects, or because we care about long horizon behavior, or because we care manipulating real objects, not just simplified polyhedrons, let's say. It's also natural that I would say that these approaches sort of have emerged or have dominated because they represent different ways of thinking about the decision, the action decision process, right? So on the left-hand side, we have approaches that are based on planning or forward search on models, feed-forward based approaches, and on the right-hand side, we have feedback-based, where we either use haptic or visual feedback, and directly from that feedback, we make decisions instead of being proactive with a model. And in the top row, I would say we have approaches that are, that make their decisions based on local interactions, right? They're trying to control or regulate local aspects of the task, like contacts, while the bottom row are approaches that are trying to regulate or control global aspects of the task, like the pose of the object. So it is natural that all of these methods or approaches sort of have originated. But the point that I wanted to make is that these perspectives, they're not alternative, right? So it's not that you can choose, you get to choose which perspective you want to use if you want to solve the real problem that is at the center, but that building general manipulation systems eventually will require us to integrating them and finding ways so that the system can reason about mechanics, haptics, planning, and vision at the same time. So one of the themes that I want to have in this presentation is that manipulation primitives allow us to simplify that integration. And I will get to these themes throughout the description in the talk, but I just wanted to present 3 key ideas that I think are important as to why manipulation primitives are important to be able to build robotic manipulation systems that eventually will integrate these perspectives. So the first thing to note is what do I mean by a manipulation primitive, and we'll get back to all of these throughout the talk, but I just wanted to highlight it at the beginning. When I say a manipulation primitive in the context of this talk and a lot of research in manipulation, I mean an interaction mode, right? So I explicitly choose how I want my end effector or a part of my end effector to contact the environment, how I want to transmit forces. And not only that, I'm going to make an assumption about how that interaction will develop, right? So something simple like I'm going to grasp an object and I'm going to assume that the 2 contacts that I'm going to make with the object are going to be sticking, right? So it makes an assumption about interaction. Or I'm going to pull an object that is in contact with the table, and I'm going to assume that the contact between the object and the table is going to slide, and I'm going to assume that the contact between the finger or palm and the object is going to stick, and that will define a control problem or its own constraints on interaction. So I'm going to make that manipulation primitive is an assumption on that type of interaction, not just an assumption on what happens with the contact, but also on what will happen with the object. Now, why? We will see that one of the key themes is that by making these assumptions, we facilitate predictability. We will, it will be easier for the system to predict what's going to happen with the object, not because it necessarily will happen, but because there will be a controller that enforces that assumption, and then there will be a planner that exploits that assumption. And it's the idea that we want to do things that are predictable, that then sort of determines what is the role of control and what is the role of planning in building these systems. Okay, so I just wanted to give sort of a preemptive explanation for what I mean by manipulation primitives, and then we will go into those more in detail in the context of the projects I wanted to describe. Just quickly before going there, the idea is that, right, so as I said, we need to build systems that try to integrate these perspectives, and to some degree, a lot of the research that has been happening in the MCube lab, it's gearing towards trying to find ways or excuses to force ourselves to integrate these perspectives. And I'll describe two today. One, how do we integrate tactile feedback with mechanics control problems, and what would be the possible role of this type of tactile feedback? And how can we use it if we want to be able to control these systems reactively? And the integration of visual feedback or visual affordances in long horizon planning. How can we manipulate or plan sequences of interactions with objects when we actually don't see objects? What we see are just point clouds in this case, or RGBD raw information. But we still want to do multi-step manipulation plans. Okay, so the outline of the rest of the talk is describing these two projects: dexterity with tactile feedback and dexterity with visual affordances. So before that, I just wanted to ask if there are any questions on the up to here. Feel free to jump in. And if not, I'll just go ahead, and I'm happy to take questions at the end.
Yeah, it looks like no questions. Thanks.
Cool, excellent. So first project, dexterity with tactile feedback. Here's an illustrative example of what is it that we want to achieve as a robotic system that in this case has two palms, that is manipulating a simple object, and it's doing it in this case through a sort of planned interaction, and we would like to be able, the robot, to do this, but in a reactive fashion, where it's constantly replanning what it should do to the object based on its perception, its haptic perception of what the object is doing. So if I go there and I perturb the object a little bit, I push it around, it reacts to sort of continue moving the object towards the goal state. I'll just say a couple more things about the system. Why do we use two arms? The basic idea is that we are interested in exploring dexterous manipulation, and you can think of these two arms with these two fat palms as a very dexterous two-fingered gripper, where each finger has full dexterity for full ability to move. Each palm is integrated with what we call a high-resolution tactile sensor that outputs an image of the deformation of a gel that is on the skin of this palm, that is directly deformed through the interaction with the object. So inside this palm, there's a camera that is looking at the deformation of this gel, and through that, we can get some form of tactile information, either geometry, for example, in this case, in the simple scenario, we can track the edge of this object, and by tracking the edge, we'll be able to understand what's happening when we're manipulating the object. Or we can also recover information proxies for that are correlated with force or shear at the interface or the slip signals. And one of the key questions that we were asking ourselves is that if we have access to this type of information, shape, force, slip, in real time, what is the best way, or what is a way in which we can consume this information in real time in the control loop, so that we can manipulate an object like this to start in a reactive fashion. And the key idea here is to use tactile feedback to regulate contact mechanics, right? And this goes back to the idea of interaction primitive, where I make an assumption that if I'm going to interact with an object in a particular way, I can use tactile feedback and a regulation control loop to enforce that the interaction is happening in the way that I assumed, right? So if I'm going to put my palm on an object and I assume that that palm is going to stick to the object, I can regulate the contact so that it's actually sticking. So one could think of partitioning the role of tactile control on one hand to control that contact, to enforce the assumption that the interaction primitive is making, sticking or slipping, and I'll show examples of both cases. And then based on that assumption, controlling the object. Once that assumption it is satisfied, not guaranteed, but at least sort of to the degree that the controller can, then I can exploit it from a planning perspective to simplify the search space as what is it that I want to do with the object. So control the contact state versus controlling the object state, and separating these two problems, and then running the two controllers simultaneously. So what does this mean, for example, in the context of this palm pushing the object in the plane, right? So on the left-hand side, you will see the object state controller that is living by the assumption that when it touches the object is sticking to the palm. It's going to follow with it wherever it goes. And then if that assumption were to be satisfied, it's very easy to move the object to the blue outline. It just needs to find like shortest path trajectory to go straight into that configuration. As you can see here, it's constantly estimating where the object is based on the feedback, and then based on its current estimation of where the object is, it's just trying to bring it to the blue outline. But there's no regulation as to whether the assumption of a sticking or a sliding, it is actually factual or not. It is just assuming that it's sticking, and wherever is the current state of the object is just constantly driving it to where it wants to go. And then on the right-hand side, you'll see the contact state controller, where instead it's just constantly trying to enforce that the palm is sticking to the object. So if it detects that it's slipping, it will press down a little bit more. You will see here the robot applying down force and the normal force increasing, and then it's leaking when it detects that it's actually sticking. So it's just in charge of regulating that contact state, which in this case is simple, but in a more general case, it could be more complex. Like, for example, in this case, there's two palms that are contacting at two corners of this object, and both palms are commanded to stick to the object and pivot this object about this point. So if there's an event that the system detects that where there's a slip event at a point where it wasn't supposed to, we can formulate a control search problem to figure out what is the optimal reaction of the system of each one of the palms, either increase the force or change their orientation with respect to the object. For example, in this case, we can formulate, we can draw the friction cones at each one of the contacts with the ground and with the palms. And then we can resolve for the contact forces at each one of these contacts that are commanded by the system. And then based on the knowledge that which would be provided by tactile feedback that this contact slipped when it wasn't supposed to, we can increase the margin of stability of this contact. We can try to make the system to bring this contact force closer to the center of this friction cone. So how do we do that? Well, we can formulate this optimization problem where these betas are just scalars that weight between the different contacts. These thetas are the margin of stability, these blue regions at each one of the contacts. And we want to maximize some notion of stability, of region of stability. And the system will search for what is the delta, or what is the change in the configuration of the palms, which in this case, it includes the forces, these Ws, as well as the orientation of the palms in that particular example. But in general, it could be all the whatever are the remaining freedoms that each one of the end effectors has. And subject to the classical constraints, force equilibrium, where the gravitational force or some external force has to be balanced by all the contact forces. This is the delta that we're applying to the configuration, and the contact, the frictional, the Coulomb friction constraints, that the normal forces have to be greater than 0, and that the tangential force has to be smaller than mu times n. So this is no different from the typical optimization problem that you would formulate in a robot that is, in a legged robot, for example, that is trying to maximize its stability when it's walking. Unfortunately, it's difficult to solve this problem in real time because the margin of stability is non-convex, right? So this theta angle has some trigonometric functions in its expressions, and also because the equilibrium condition is bilinear, right? So we are looking both for what are the forces that we should exert on the contacts, as well as the deltas of the Jacobians of the Grass matrix that are defined by the multi-contact formation. And because we're looking for the values of these two things, this constraint is not is bilinear, so it is difficult to optimize. So in practice, what we do is we find like a convex approximation of the margin, which I'll show in a second, and we linearized around the current the previous configuration of the system. And the convexification of the margin, instead of using this angle, we use this distance alpha, which now is a straight projection. So it doesn't depend on the trigonometric function. This is a classical trick used by the locomotion community. And then we just linearized around the previous configuration so that the equilibrium constraint now becomes linear. And by doing that, we can solve this optimization problem in real time. And then we can apply it here. So now here, what you see is a classical regulation behavior, right? Where both the object state controller that is trying to bring the object to the center and tracking it with tactile feedback, and the contact configuration controller, in this case, just pushing more or less on the object, are working synchronously to maintain the object in that outline configuration. Or we can apply the same formulation to now track a trajectory, not just a regulated single configuration. But now you'll see in this the grasp, if it detects that the object is moving, well, it will decide to apply more force or less force, and it will correct to be able to bring the object to the desired configuration. And that's this project has served as I would say a baseline for a lot of the work that is happening now in the group, where this idea of developing controllers that use tactile feedback to regulate contact configurations, which could be in the context of, in this case, a bipalmar system, or could be in the context of grasping an object. How do you make sure that you have a closed loop grasp where if the robot is grasping the object and you push against the object, the robot will hold its ground until it detects that the object will slip, and then it retracts, right? It doesn't want to lose that stable grasp or that contact formation on the object. Or regulating more recently external contacts. So if the robot is grasping that object and is trying to put it down and place it gently, the moment that it makes contact with the ground, how does the robot understand what's happening with that contact with the environment? How do we regulate that contact? It turns out that tactile feedback, this type of tactile feedback, plays an important role in enabling that capability, even without knowing the shape of the object, so that it can operate at a high rate or as a low level controller. And here's a sort of a summary of the idea, right? So regulating contact mechanics, which is sort of the high level goal that I think that tactile feedback can play in a robotic system. Which contact mechanics it needs to regulate? Well, that's dictated by the interaction mode that the primitive is defining, and it's done by sort of partitioning the role of the control by enforcing a particular assumption and then exploiting it to manipulate the object. So in the case of this Palmar system, in practice, what we have is an MPC controller that monitors the grasp stability or the multi-contact formation, the stability of that multi-contact formation. And then on top of that, there's a primitive controller that depends on the type of interaction. It just directly moves the object to where it has to go. And we've also applied the same idea to other systems, like in this case, manipulating a cable. How do we get the fingers, these tactile fingers, to slide along a cable in a stable manner? So to go to the end of the cable and then insert the connector, for example, in this iPod here. But the interesting control problem here happens in the ability to slide the fingers without the cable sliding outside from the fingers or falling. And without going into the details, because there's no time, the basic idea here is that just like in the context of manipulating rigid objects, by constraining the interaction to a particular type of contact mode, in this case, sliding, we can formulate a control problem that is in charge with making sure that the frictional interaction between the cable and the fingers is such that it is easier for the gripper to slide its fingers along the cable and control its position. So this is the type of feedback that you get, right? So we can estimate the pose of the cable as well as get some sense of the shear forces when the cable is sliding. And the range of dynamics or frictional interactions that can happen between the cable and the fingers is very large, but Instead, what we do is we define or we build a controller that is regulating the gripping force so that the frictional force between the cable and the fingers is always maintained within a certain bound, within a certain range that we saw that it was useful for the sliding. And independently of whether the cable is thicker or thinner, or it's more rubbery or made out of cloth, there's a gripping controller that is regulating the gripping force at a high frequency so that it's always constant within certain range. And by doing that, then it's much simpler to write the parallel controller that is in charge of sliding the fingers while maintaining the cable in the center of the fingers, right? So this would be the regulating controller, just a proportional derivative controller that doesn't like these tactile imprints and doesn't like these tactile imprints because there's too much friction and is always trying to keep it within certain range. And then with just a simple linear controller, we can predict what's going to happen with the cable when we're pulling from it. And just with this LQR controller, then we can, it is possible to slide the fingers in a stable fashion along the cable. So very, very different system, but the same philosophy of having a controller that regulates the contact mode that we would like to have, we would like the end effector to have with the object, and then exploiting that for being able to plan through simpler dynamics. So that's the let me see how am I doing on time. So that's the first part of the second part of the talk. How do we think about integrating tactile feedback in mechanics control loops, and what is the potential role of tactile feedback in dexterous manipulation? The idea of using tactile feedback to regulate contact modes, to make contact behave the way that we think it should, instead of letting contact behave the way that it does. And I want to switch gears, and I'm going to look at the same system or the same problem, but instead of worrying about the local aspects of the decision process, I'm going to worry about the global aspects of the decision process. How do we control the state of an object from one configuration to another configuration, and plan through this the strategy or the sequence of steps, like in this case, understanding that first the palm has to move the object forward, and then, because it wasn't possible to do a grasp due to reachability, and now it is in a configuration where it can actually grasp the object and upright it, but doing it in a way where we are not directly exploiting the model of the object. We don't know what this object is, but rather just directly through the information that we get, the raw data that we get through a depth sensor in this case. And the inspiration for this project comes from back in 2017 when we competed in the Amazon Robotics Challenge. And several years before that, the community has been embracing this approach to manipulation, where instead of directly doing a state estimation and then based on that plan a sequence of actions, develop these systems that are directly guided through visual feedback, visual affordances, right? So in this is a system that competed in the Amazon Robotics Challenge that is tasked with picking up all of the objects on the left bin and putting them on the middle bin. And it has never seen these objects before. It doesn't even know what an object is, or it's not doing any explicit segmentations of the objects. The only thing that it has done, or that it did, was learning the appearance, both in color space as well as in depth space, of objects that are suctionable or objects that are graspable. And then just deploying that model that is constantly going to pick up the thing that is more that has the appearance of the most graspable thing or sectionable thing in a loop. And this type of approach to manipulation has definitely, way before this work, has sort of been embraced by a large part of the community, and in part because of the ability of neural networks to learn from many examples, right? So capture prior information in a free-form way, and with that comes the ability to generalize to many different objects. And that's something that was an inspiration to us. And here's just like a quick rundown of how the system works, right? So these are the inputs to the system, RGBD, and there's two neural networks that are directly predicting what are heat maps on these images as to what are the locations of the most likely objects that look like they should be graspable or sectionable. And in this case, the top point in the heat map is this point here that corresponds to the handle of this whisk. And the robot goes and successfully picks up that object, but it doesn't, again, it doesn't even know that it's an object. It has never seen a whisk. It doesn't know that that's a handle. It just has experience in the past that grasping objects that have that geometry and also that are uncluttered around it, it has led to a successful grasp. So it's able to generalize and make that prediction. So
can I ask a quick question?
Yeah, excellent.
When it was trying to pick up the notebook, it failed because there was something on top, and then it failed again, and it moved around. And I'm wondering, is that did it just perturb the situation randomly, or is there any actual planning involved in that decision?
Randomly, I guess you're referring to.
Well, I'm saying it tried to pick up the notebook and it failed
several times, right?
And then, well, the first time it fails, it ends up picking up the thing on top of it instead. Well, there was a previous.
Actually, it picks 3 times. Yeah. But that's a great example for what I want to describe today, which is that these systems or this type of capability, and thanks for bringing it up, it has no notion of object, right? So it doesn't have the ability in any way to reason about the fact that there is something on top of something else. And that if that something else were to be heavy, you might be better removing the first thing that is on top and then picking up the second thing that is at the bottom. Or that if there's something heavy, it might be better to pull something rather than pull it directly up. In this case, it just works through because of iteration, because of looping. But I do believe that it is important to have that ability to forecast or plan or predict what's going to happen, so that at least the system is capable of thinking ahead 2, 3, 4 steps to be able to do more complex and dexterous manipulation. And that's one of the things that has been driven some of the research in the group. How do we combine this type of perception that has huge value in terms of generality over objects with the ability to plan multi-step actions? So that this is a very complicated case because there's many objects that are have very difficult dynamics, like deformable objects, but so that you could decide to first, I'm going to pick this thing, so that, and then I'm going to pick the other thing, but without having to do or know the models of the objects beforehand or do a state estimation. So the ability to plan sequences of actions, but still within these more vision guided approach is something that we've explored for some time. And here there are 2 example works where there is some multi-step manipulation, but where the sequencing is not explicit. And I'll say what I mean by that. In this first case, the system is tasked with picking up all of the objects and putting them in this box, and is capable of learning over time. It has learned through experience that the way that these objects were stacked on the side on each other, it was not possible to pick them up. It had to push them apart, and then it will be able to pick them up. So it first pushes them, and then once it's possible, it picks them up and puts them. And you'll see now it fails, or it doesn't at the optimal thing. It will push the object, but now it will plan again and it will pick up the object. But something important, there's no explicit planning here. This system has been trained with reinforcement learning, and it will run again through over and over. While it does have some explicit reasoning both about pushing, so here there is an affordance model, as a neural network that creates the affordances for where it makes sense to push objects. And here is the same, but for grasping, where it makes sense to grasp objects. This part of the network is basically the same network that I showed in the picking system in the previous slide. But now it has the ability to make two decisions, either push an object or grasp an object. It doesn't know what's going to happen after executing any action, but instead it's trained with reinforcement learning. So it just comes up with a policy and it deploys it. And with some receding horizon, it rewards whether it eventually is able to pick up objects and put them in the box. And there's sufficient signal in that sequencing of pushing and grasping to eventually train both the pushing network and the grasping network, right? So this system is rewarded just for either one of two things. One is a very small reward for changing things, and second, a larger reward, much larger reward for picking up an object successfully and putting it on the box. And just with that, through in the order of 2,000 iterations of trying to pick up and push objects, it successfully learns these two networks that when deployed, they provide sort of whatever is the highest point of any of these histograms is the thing that it's doing. But again, there's no explicit forward prediction of what's going to be the outcome of an action other than just through that reward that that is predicting. And similarly, and I guess this is the work that Kevin was referencing to with tossing bot. This system has also learned in this case to, let me stop this one, to pick up objects and toss them into specific boxes. And in this case, the system has to learn both to how to grasp the object or which object to grasp and in what configuration, as well as a residual model for how to throw them into a particular box. And there is no, again, explicit planning as to how to sequence those two things, the picking and the throwing. But again, both are trained through just the experience or the reward of, is this an accurate toss or not? That is a sufficient signal to be able to train the residual model for how to toss, as well as how should we grasp an object so that it is possible to toss it accurately. So again, it's a slightly more complex, but still structured neural network that is trained now in this case with just self-supervision.
One
just
other
from that
question
signal.
here.
Yeah.
Does it, when it's tossing, does it move to the same position to toss from, regardless of where it picked it up, or does it toss it from wherever it picked it up, so to speak? Does that make sense?
So I think in this, yeah, it makes sense. In this example, it moves to the exact same position and it tosses in different directions and with different velocities. We've done experiments showing that the way that it's coded, it doesn't matter as long as the robot control is accurate enough to produce similar velocity profiles if it's executing a trajectory in this configuration or in this configuration. So it's programming Cartesian control, where it's actually is capable of, for example, be trained on tossing objects to just some of these boxes and then tell it to throw to other boxes that it hasn't thrown before, just because it's sort of it's capable of just transporting the throwing trajectory into those other boxes.
Great, thanks very much.
Cool. But again, it's a system that it is not capable of doing any kind of forward forecasting as to what's going to be the outcome of an action. So it would not be capable of sequencing two actions. For example, I'm going to pick up an object and then re-grasp it into a grasp that would allow me to toss it better. And I do think that that is an important capability for dexterous systems that want to do more complex behavior, some form of forward simulation or prediction of state. And here's an example where that would be important, right? If you want the system to be able to move this box from here to here, but it doesn't know that it's a box, right? It just sees like a point cloud. How would a system be able to predict that? First, it has to pull the object to the center so that it is a configuration that is reachable by both arms so that it can change the face of the object that is in contact with the ground and place it down and then pull it to the side with the other palm. This is an action where there's a longer term explicit strategy that is important to the task, and that it requires some degree of forward prediction to be able to decide what is that sequence. So this is the kind of problem that we've been looking at, stemming from the previous works, and see if it's possible, if there's a way to do this, but still with affordances, so that we could do this not just for a cube, but for a more complex object. And the basic idea, it goes back to the notion of contact regulation and assumptions in primitives, is that if we prescribe ourselves to interaction modes that, in this case, for example, that are producing a sticking interactions with the objects. If I'm going to push or pull or grasp and place the object, if I make the assumption that the object is going to be rigidly attached to the gripper in any of those interaction modes, then the forward prediction is much simpler, right? So I don't have to simulate it. I just have to, for example, in this case, apply a rigid transformation to that segment of the point cloud that I'm manipulating. And after manipulating that segment of the point cloud, I can think of that new point cloud again as a new observation and deploy my my policy or my planner. Based on that idea, what we've done is generalize this notion of affordance, where we built a model that it's capable of predicting. It's a generative model that is capable of predicting not just where to put what is it a good idea to put the gripper or the suction cup in the previous examples, but also what are the possible new locations where the object could be after the gripper has interacted with the object in that way, right? So it generates two things. One is possible interactions with the object, and second thing is possible transformations that the end effector will be able to apply to the object, given all of the underactuated mechanics of that interaction mode. So we learned that system in simulation and from experience, right? This is a simulation with just cuboid objects, where we constantly are spanning a cuboid and then a rigid transformation. And then the system is trying to figure out whether it can actually pull it. This is just learning the pulling affordance into that configuration. And this generates a sequence of point cloud observations of the object, as well as successful contact locations with that point cloud and successful transformations of the object. And that is sufficient to learn a generative model that now given a new point cloud, it will be able to predict contact samples. Where is it possible to put the palms, and where is it possible to bring the object? And then this sort of affordance model now, that is not just a histogram or a heat map in visual space as it was before, but now it's a sampler of where it makes sense to put the palm or the grasp, and where is it possible to move the object, becomes just a sampler that we can input into any normal regular planner, sampling-based planner, like RRT. So for example, we tell the system, move the object from here to here, and what you have to do is, and we pre-specify this sequence of actions. First pull right, and then reorient the object, and then pull right again, and then place it on the shelf, and then pull it to the left. But it has to decide where exactly to put the palm, given my point cloud observation, and how exactly to grasp the object, and where exactly to put it on the shelf, and then how exactly to move it to the final location. And it's capable of doing that. The problem of predicting the strategy, that's something that is also possible to learn or reason or search through in simulation, but it's a more computationally taxing problem, and it's something that we're very interested in. And again, because of the reliance on these visual affordance models that are capable of producing more generality, right? So if we've trained a system that is capable of manipulating all of these cuboids of many different aspect ratios, there is some hope that it will be able to manipulate not just those specific cuboids, but it would generalize to slightly other objects. So here's just produces this plan to manipulate these this bottle. Here's just
Alberto,
an example on a real system.
We're going to,
yes,
Alberto,
excellent.
Try to finish up next minute or two so we can have time to ask you lots of questions.
Excellent. Yes, sorry. That was the last slide. And the key role of primitives in enforcing contact modes, and the key role of primitives in simplifying predictability so that we can do simpler planning. So this is the last summary slide. Right, so a manipulation primitive is a model that makes an assumption on interaction and prediction, both. And then there's a shared responsibility from the controller with tactile feedback and from the planner to be able to enforce the assumption on one hand, and to live inside that assumption, to only do things that respect that assumption. So that in practice, we only do things that are predictable. So that's the end of the talk. Thank you very much. I'm gonna stop sharing here, and I'm happy to take any questions or go back to the slides if necessary.
Great, thanks very much, Alberto. Any questions? I'm just going to hand the mic to you. So does anybody have a question, or anybody online? Question over here. Alberto, I don't know how far you can see, but why don't you come over here?
Yeah, I can see there.
I just had a question about scalability, because you mentioned earlier about the palms of the robot, to think of those as 2 fingers of a gripper. And so if we wanted to get that down to the scale of a gripper, you know, what are some of the roadblocks and challenges that one would have to address to get it to that size?
Yeah, we have much smaller integrations. I guess I didn't show this slide. But these are fingers with the same type of technology that produce, actually, this is a much higher quality type of feedback now than those palms. In fact, those palms, we make them bigger because we wanted to use palms. But I think that there has been a lot of progress in reducing the scale of, this is GelSim 3.0, the latest version of the sensors we've done in the lab. But there's been a lot of progress in integrating this type of sensing technology in smaller form factors, making them compliant or bendable so that it actually acts as real skin. So if you want to have articulation, I think that that's more of a challenge still. But I think in terms of scale, I'm comfortable with what we have.
Hi. So I'll get there. Okay, my butt's not in your face. So I have a question with regards to the coordination between the two hands. In this case, obviously the two hands seem to be very aware of what each other was doing, being controlled by same thing. I was just wondering if you had any thoughts on if the hands couldn't talk to each other, if it was two robots that had to cooperate, or if, for instance, you had 1,000 robots that had to cooperate, and how this work might be adapted towards that.
Yeah, that's a great point. I think that there is, if the two robots have palms only and they're independent, I think that that's a very complex problem, because the type of feedback you get on just one palm is just one-sided, so there's information that you're missing. If you're grasping it with a gripper, I think that you would get a bit more information, and to some degree is not too different, maybe less antagonistic than the case where you're trying to control contacts with an unknown environment, right? So imagine that you're inserting an object into a hole, and the hole is producing contacts on the object, and is pushing against it. How do you reason about those contacts? That is a problem that I'm very interested in, and that we've thought about for a while. In part because I think that this type of tactile feedback is an enabler for that type of problem. I think that the old question of what kind of information you can get with tactile sensing that you might or might not be able to get with force torque sensing at the wrist, I think that some of that has to do with the ability to estimate or reason about external contacts. And you can think of the other person as an external contact, if it's an adversary. If you want to collaborate with that or cooperate, I don't know how you would write that control or decentralized control problem.
Thanks, Albert. And last question, anybody have one more question? Yep, Juan.
So first of all, thank you, Professor. You gave us a great talk, and we learned a lot. And my question is, you showed us some grippers with two sensors mounted on both sides. So for some simple manipulation tasks, I can imagine that the information you get from both sensors are pretty similar. So do you think we can get some benefit from having both sensors on each side, or is it possible to use only one sensor to do that?
I see.
Thanks.
Yeah, that's a great point. If the object is completely rigid, I think that you're right that in theory, with just one sensor, you should be able to get the same information. One problem, however, is that the kinematics, I don't know if kinematics is the right word here, but the Jacobians of your sensed information, right? So the function that goes from motions of the object that you're grasping to how much your sensors are changing, right? So the observability that you get when you have two sensors, it's much larger, or it's much better conditioned than if you only have one sensor, right? So imagine that you're grasping an object like this, right? And if I perturb this object and I'm only sensing what's happening here, there are motions of the object that might be okay to sense here, but there might be motions of the object that might be difficult to sense here. If I combine both observations, I get a better conditioned like observability metric. I don't know if that makes sense. But we have done experiments using either one or two sensors, and in theory, you get the same information. In practice, it works better when you use both. That's what we've seen.
Alberto, that was just great. Thanks so much for your seminar. I'm going to wrap it up here so that we have a chance to ask you some questions.
Yeah.
We're gonna retire to a smaller room where we can be a little bit more intimate. But thank you so much again for a fascinating seminar. Lots of great work here, a lot to unpack and a lot to discuss further. So thanks again.